So let's see. Yeah, we talked about thermal energy and heat and such last time we met on Monday. And of course, this unit is talking about thermodynamics. The word dynamic means kind of change and flux. And so we'll be talking about heat, even though we can't see it, obviously, if you have a temperature. And I bring thermometers again today, but if I have a thermometer, I can kind of touch this material or touch this material. They have flat thermometers, you know that? Actually, thermometers, you can get the surface temperatures if it's on liquid. But that is just an indication of the heat. Remember, heat and thermal energy are synonyms. Temperature is not. Okay, so here we go. This is how this works. So, for instance, I have these two. I have a cup of water and I have a bathtub full of water. And say they're both at, let's see, water boils at 212. So say they're at 190. I don't know, maybe that's pretty hot. I don't know. Nice hot. Okay, hot water, hot water. So I think you guys answered this question before. They're at the same temperature, so my thermometer reads the same, but which one has more thermal energy, the cup or the bathtub? The bathtub, exactly. And why is that?
It has more.
Because it has more.
Because
it's dependent upon the amount, exactly. Oh, is it intensive or extensive? It's dependent upon the amount. It is extensive. Yep. It is extensive, because I was thinking intensive independent and extensive dependent. Yes. Yeah, very good. So the three things are temperature, amount, so we got that with the bathtub. But the other thing is, and I don't know how to kind of do, I guess I could do an example like this. I don't know. If instead of water, if we had, I think we're going to see the information coming up here to convince us of this, but if instead of water at 190 whatever Fahrenheit, we had methanol at 190 Fahrenheit, honestly, the methanol at the same temperature, same mass, would have less thermal energy. It's because of the specific heat of methanol versus the specific heat of water. So the third criteria, one is the temperature, how fast those little atoms or molecules are moving. The other is amount, and then the other is something we call specific heat. So you're going to hear me call it specific heat, but specific heat capacity, they mean the same. Okay, and you look this, and I'll even write it down. You look this, how do I say this? You look this up. Look it up. Google it. Okay, if you want to know the specific heat of anything for a problem, and every once in a while I'm working problems for your answer key, I'll just say specific heat of iron. Okay, and there it is. Of course, there'll be specific heat of iron in its solid state, in its liquid state, and heaven forbid we can get iron into a gaseous state. But the different physical states of the material will give it different specific heats too. All right, so we need to talk a little bit more about specific heat. Specific heat capacity mean the same thing. Do you remember the other day when I said, this will get you down the road? I drew a little box. I drew two little boxes. But this little box is going to be 1 gram, exactly 1 gram of H2O. And you remember I said we're going to go from 14.5 to 15.5 degrees Celsius. And I said we're going to zap it with 1 calorie. And that's actually the definition of a calorie. Okay. So here we go. Specific heat capacity. The amount of heat needed to raise the temperature of 1 gram of material 1 degree Celsius. Is that a 1 degree Celsius change? So we've already kind of talked a little bit about this idea. So actually, water in its liquid state, so this is H2OL, liquid. The specific heat, the symbol for specific heat is this. Specific heat, I don't know why, a big C, a subscript P for H2O, liquid, is 1.000 calories per gram to raise it up 1 degree Celsius. That's specific heat of water. It's liquid state. Okay. Does anybody remember the relationship between 1 calorie is exactly equal to how many joules?
4.1.
Yay, 4.184 joules, exactly. So I could change this to 4.184 joules, and I could change this to 4.184 joules per gram of liquid water, raising up 1 degree Celsius. It's all the same diff. Totally, totally, totally. So units are energy to zap. So I actually picture this. You know, thermodynamics, this topic, I picture my little squiggles are thermal energy. So zapping it with thermal energy, that amount per how much you're zapping, per how much the temperature is going to change because you're zapping it. Do you guys remember what's the relationship? How do I say this? I want to go Celsius and Kelvin. Well, let's try it this way. Anybody know what 0 Celsius is in the Kelvin temperature scale?
273.
Very good. 273 or 273.15, depending upon, I think there's even more digits after that, but that'll give you 5 sig figs. Perfect. And the cool, no pun intended, the cool thing is as we step down into negative degrees Celsius, we are approaching, in this case, 0 Kelvin. So what temperature is the Celsius temperature at 0 Kelvin? By the way, each unit on the Celsius scale is equal to 1 unit on the Kelvin scale. So step, yeah, exactly. And that's where I complained, remember the other day, need to get Neil deGrasse Tyson on the phone, that that you can't have negative 300, right, Celsius. Where was I? Oh yeah. My point is since these units are the same, and we are talking about a change here is equal to 1 degree Celsius. Do you buy this, that the change here is also equal to 1 unit Kelvin? It's just a beautiful. Both metrics would kind of come full circle. So honestly, since that's a degree change, how do I say this? The specific heat of liquid water is also, and I'll just pick on joules per, is 4.184 joules of energy per 1 gram of liquid water to raise it up 1 unit on the Kelvin scale. It's the same thing. So interchangeable. Then this one right here is probably my least favorite. You know, it's the least descriptive. Joules of energy per gram per degree Celsius, because I like to think of degrees Celsius as in the denominator, I suppose. This one's not bad. This whole raised to the negative 1 power means it's in the denominator raised to the first power, so that all works. Okay, all right. So this is just what I said. If a step on the Celsius scale is equal to a step on the Kelvin scale, and you're talking about steps anyway, then, hey, they're actually, the specific heats are interchangeable. Energy per gram degree Celsius, energy per gram Kelvin. By the way, if you want to be really cool, no pun intended about this whole thing, is when you talk about the Kelvin temperature scale, don't say the word degrees. It's Kelvin units, not Kelvin degrees. Not sure why, there's a reason for that. All right. So here are some specific heats. These I mentioned Google. So we could Google what is the specific heat of ethanol. And I don't know if that was the one I picked on, but let's just pick on that one. Maybe it's on the next page. Ethanol. So can you see where I can make another box? And instead of water, it's going to be liquid ethanol. 1 gram ethanol. I abbreviate ETOH just because I'm lazy. It's in its liquid state. We are going to zap it. Notice instead of zapping it with 4.184 joules per gram degree Celsius, I'm going to have to only zap it with 2.376 joules of energy to get it to go from 14.5 to 15.5. Okay, so it's easier. It's easier to zap. But you need to think of it this way. They both have the same mass. This one's easier to zap than that one, water versus ethanol. The thing about it is once it's zapped, this actually it holds less heat. It's easier to zap, it holds less heat. It retains less heat. Water, harder to zap, it retains a lot more heat. Actually, our planet is really into this whole thing with water, the 4.184 joules to raise 1 gram of water up 1 degree Celsius. That's a crazy big number. If our planet didn't have that liquid water, that's a player in a lot of things. Okay. All right, so here's some other things. So, I mean, check it out. Lead, things you're like, I don't know, I don't hold a lot of lead. I've got some lead shot in the lab and all that. But look how easy it is to change its heat or change its temperature. So you only have to zap with 0.130 joules, zap 1 gram of it to get it to budge 1 degree Celsius. That's what that constant means. It's weird to think of these gases, because to get 1 gram of these gases, it's kind of a tricky thing, you know. We could do that. Keeping its gaseous state, you couldn't really compress it too much, or you change it from a gas to a liquid. Here's some other constants. So the 4.184 is kind of an outlier. 4.184 joules per gram degree Celsius. It's pretty darn high. Okay, so I brought along a couple of objects. These are props. So this is wood, okay, and I don't know what kind of metal this is. So I have in my notes, we'll just kind of take an average of the metal, and then we'll go with a specific heat of about 0.7. So about 0.7, okay, 1.8. And how do I do this? Like if I were just to come around and to ask you to put your hands on, you know, one of them, what's your hand going to feel like on the metal? Colder. They're similar masses. What does it mean if it feels cold? What does that mean about the energy transfer? Does it mean that it's transferring much or it's not transferring much? It is, yeah. Yeah. So when I use the word stubborn. So the 1.8 versus what I say, 0.7-ish or so. So this is 1.8. This is 0.7. Does it make sense that this is like, dude, I'll take the thermal energy and I'll go ahead and heat up real quickly. This one's like, you can put your hand on me, but I'm not going to really, I need 1.8 joules of energy before I'm going to change my temperature. Okay, so that's kind of how that works. They are kind of similar in mass. That matters because that's where you're touching it, but these may or may not help you on exams, on your homework, these little tables. So just do your best. On a test, I will usually give you the specific heat. Although I think we're going to do an example next week that shows you how you can calculate your own specific heats given information, certain information. Okay, notice that these are energy per gram Kelvin. Same thing as energy per gram degree Celsius. Okay. Oh, this is energy per mole. Those could be helpful. We can go back and forth between these two using what? The molar mass, right? Okay, so here we go. We're going to do a couple of just general thought exercises, and next week we'll see how we can kind of actually come up with these numbers. But does this make sense? We have two substances. We have copper and aluminum. Which one's more stubborn to heat up? Yep, the aluminum is more stubborn to heat up. We're going to do two sort of thought exercises. In this case, the masses are the same, and we're going to take them to the same, we're taking from the same initial to final temperature. What's the temperature change? 30. Temperature change is 30.0 degrees Celsius, exactly. Okay, so if we, let's see, energy, yeah. If we, how much energy, which one's going to take more energy to go 30 degrees? How many people think the copper will take more energy? How many people think aluminum will take more energy? Me too. Exactly. Now that Q, again, we'll talk next week what Q means, but Q means it's the energy change. So Q means change in energy. So yeah, we have to zap it with more energy. Exactly. This is kind of a thought exercise. And we'll kind of get to those numbers next week. Here's another thought exercise. So in this case, we are zapping them with the same amount of energy. Again, we have copper that's less stubborn and aluminum that is more stubborn. So we're going to zap them both the same amount of energy. They're going to both start at 20. Which one's going to get hottest? How many people think the copper will get hottest? Yeah. Exactly. So that's kind of what, when we're talking about thermodynamics, that is the change in thermal energy of an object. Sometimes you have object A and object B swapping thermal energy. In this case, you just have object A getting zapped with energy. Okay. Well, very good. So this slide says you need to memorize these two constants. Well, for water. And notice I don't like this convention. I would rather go calories per gram degrees Celsius, or remember degrees Celsius, degree Kelvin are interchangeable. These are the same things I put on the board. Units here would be 4.184 joules per gram degrees Celsius or Kelvin, same thing. All right. So one more thing I need to talk about, and actually this is my second time to teach out of this OpenStack textbook, and when I taught it out of Patrici most recently, we didn't talk about this other thing called heat capacity. So, try not to butcher it. So specific heat or specific heat capacity is what you look up. That's C sub P. Now there's this other thing that you can't look up, and it's called the heat capacity of an object. And I have a couple, I'm going to kind of use this as an example. And actually, we could use, a minute ago we saw the cup of water versus the bathtub of water. And you told me the bathtub of water would have more thermal energy, and you're right. What you described was the heat capacity of that body of water versus the heat capacity of the cup of water. So I brought this, like if I put these two together and they have a certain heat capacity, if I look at one of them, it has a different heat capacity. Now together they have the same specific heat, which we went with 1.8, okay? So heat capacity, I think it says over here. Well, that's an example. But heat capacity is then extensive. Heat capacity is extensive, yeah? It depends on amount. So to get to heat capacity, which I just, like goodness, feels a little foreign to me, because I don't remember covering it this way years ago in this class. But to get to the heat capacity, all you got to do is take the mass of the object in question and multiply it by the specific heat that you look up. So it's not too bad. It's kind of nice. It makes sense. So if we were to take these two pans that are made of the same material, and I don't have the C sub P, I don't have the specific heat for these. But it's kind of like the bathtub would be on the right and the cup of water would be on the left. So which one has the most heat capacity, the left or the right? The right, yeah. Which one has the highest specific heat? They're the same, yeah. They're the same specific heat. The same specific heat, you look it up. Or heat capacity, yep, you got it. So yeah, intensive independent of amount. So intensive of those two would be the specific heat or specific heat capacity. The C sub P, the thing you look up. It's intensive of amount. And then of course the heat capacity depends on amount, so it's extensive. See you tomorrow. That's how far I wanted to get. Okay. So if you haven't started yet, you might want to start in on those problems in unit 2. I think they can help.